Welcome back to The Explainer. I'm your host, and today we're tackling a subject that is, well, famous for causing confusion, anxiety, and maybe even a little bit of heartbreak: quantum physics. But here's the secret. It's not just some weird, distant outpost of theoretical science. It is literally the most successful scientific theory of the last 100 years. And its weirdness? It secretly powers our everyday modern world. Everything from the smartphone in your pocket to the exact way we keep global time depends on this invisible engine of the quantum realm.
Okay, let's dive into this. And let's start with one of the most brilliant minds in human history. Albert Einstein famously looked at the emerging theories of quantum mechanics and declared that he didn't believe God plays dice with the universe. He was deeply, deeply skeptical of a reality that operated on random chance. And yet, despite his doubts, quantum physics has proven itself again and again with uncanny accuracy, ultimately creating the very world we live in today.
So to demystify this famously intimidating subject, here's our roadmap. First, we'll look at the quantum revolution. Then, escaping the clockwork universe. 3, keeping perfect quantum time. 4, lasers and gravitational waves. 5, the power of entanglement. And finally, our quantum future. We're going to take this step by logical step, so let's get right to it. Starting with Section 1, the quantum revolution. Our story really kicks off back in the 19th century, when scientists realized that light sometimes behaved like a continuous wave, but other times it acted like a collection of miniature billiard ball-like particles. This totally broke the mold and led to a completely new kind of physics. See, in the classical, Newtonian world, the universe is deterministic. It's like clockwork. Even things that seem random, like rolling dice, are actually completely predictable if you just know the exact initial math and forces. But quantum physics, it tosses out that certainty entirely. It tells us that probability is intrinsic to reality. Even if we know absolutely everything about a setup, the best we can do is predict the percentage chance of a certain outcome. We're essentially trading absolute certainty for probabilities.
Which brings us to Section 2, escaping the clockwork universe.
That probabilistic nature leads us to a really strange reality when you think about what happens when no one is actively looking. This introduces a concept called superposition. When we aren't observing a particle, like an electron, for example, it can only be described mathematically as a wave of probabilities. It exists as a combination of all possible outcomes all at once. But the exact moment it's observed, that wave function collapses into one specific location. And honestly, even professional physicists struggle to wrap their heads around how external realities seems to fundamentally depend on the observer making a measurement. And this brilliantly illustrates just how wild the quantum realm gets, especially when we apply it to the cosmos. Quantum physics tells us that seemingly empty space is actually seething with particles and antiparticles that appear, do a little dance, and then annihilate each other. In 1974, Stephen Hawking theorized that if this happens right at the edge of a black hole, one particle might fall in, while the other manages to escape as radiation. Over unimaginable timescales, this tiny quantum leak actually causes the black hole to evaporate. So the physics of the very small can actually vanquish supermassive monsters. How crazy is that? Moving on to Section 3, keeping perfect quantum time. Now, quantum physics isn't just about cosmic behemoths and black holes. It governs our everyday lives, and nowhere is this more intimate than our relationship with timekeeping. Think of time like a perfectly synchronized tango dance. It absolutely requires a flawless metronome. Historically, we track time using the sun's movement, then in the 17th century we used pendulums and springs, and eventually vibrating quartz crystals in the 20th century. But since the 1960s, modern time has been officially determined using the quantum rules of atoms. Specifically, a single second is defined by counting over 9 billion oscillations of the resonant frequency of a cesium-133 atom. Because the laws of quantum physics are unchanging everywhere in the universe, it gives us a perfectly universal time. You might not even realize it, but you depend on this quantum timekeeping every single time you pull out your phone. The Global Positioning System, GPS, relies on a network of over 30 orbiting satellites, and each one carries multiple atomic clocks. When you use a map app, your phone is receiving time-stamped signals from these satellites. By calculating exactly how long that signal took to arrive, it triangulates your exact position to within just a few yards. Simply put, without quantum-based atomic clocks, we literally couldn't navigate the modern world. And today, we're taking timekeeping even further. Physicist Jun Ye has built optical atomic clocks using strontium atoms that are 100,000 times more precise than our standard cesium clocks. To put that into perspective, they are so incredibly sensitive that if you raise one just the height of a single human hair, it will actually detect that time is running slightly faster due to the very subtle weakening of Earth's gravity. That's a phenomenon called gravitational time dilation, measured over the height of a hair. Absolutely amazing. Next up, Section 4, lasers and gravitational waves. Those highly advanced clocks we just talked about, they rely on a piece of pure quantum technology born back in the 1960s, the laser. To understand why a laser is so incredibly special, just look at an old-fashioned light bulb. It heats a filament which excites atoms to vibrate and emit photons in all directions across all sorts of different wavelengths. It is pure thermal chaos, kind of like a chaotic mob of people at a rock concert singing at entirely different pitches. A laser, on the other hand, is like a Juilliard choir. It's a million trillion voices singing the exact same perfect pitch in the exact same direction. Let's move to and see how this builds step by step through a quantum process called stimulated emission. First, an electron sits in an excited high-energy state. When a photon of the exact perfect frequency passes by, it triggers that electron to drop its energy and emit a second, completely identical matching photon. When you place these atoms between mirrors, those photons bounce back and forth, stimulating even more emissions. It's a massive quantum mechanical amplification process that creates an intensely pure beam of light. And that pure beam? It's the ultimate measuring tape. The LIGO Observatory uses ultra-stable infrared lasers, splitting the beam down two 2.5-mile arms set at right angles. If a gravitational wave, which is a microscopic ripple in the fabric of spacetime caused by the most powerful events since the Big Bang, like colliding black holes, passes through Earth, it slightly changes the length of those arms. In 2015, LIGO detected exactly that. It confirmed Einstein's once doubted theory of gravitational waves and gave us a completely new way to observe the universe. All right, let's head into Section 5, the power of entanglement. Now, what's really interesting about this is that we are arriving at arguably the most confusing yet powerful aspect of quantum mechanics. Einstein derided it as spooky action at a distance, but it's undeniably real. We're talking about quantum entanglement. Imagine a machine spitting out pairs of magic coins. You flip them, and they both come up heads. You flip another pair, both tails. It happens every single time. To test it, you send one coin all the way to the moon and flip them simultaneously, yet they still perfectly agree. In quantum mechanics, particles can share a state so deeply that they act as one single entity, completely instantly connected, regardless of the physical distance separating them, no matter how far apart they are. And this spooky entanglement is now being harnessed for modern computing. A classical binary bit is like a simple light switch. It is strictly set to either a 0 or a 1. The whole shebang of modern computing boils down to these tiny switches. But a quantum bit, or qubit, operates via superposition. So instead of a switch, think of a sphere where a qubit can exist anywhere on its complex surface. By entangling multiple qubits together, you generate computing power so incredibly extravagant that describing just a few hundred entangled qubits would require writing down more bits of data than there are atoms in the visible universe. Let that sink in. Tech giants like IBM are building the hardware to actually harness this. But if you look at IBM's quantum system too, you might be a little surprised. That beautiful, shiny, golden chandelier you often see in photos, it's not actually the computer itself. It's a dilution refrigerator. It's essentially a massive, highly specialized freezer designed to cool the tiny quantum chip to near absolute zero. It literally has to be that insanely cold to protect the fragile superconducting metal loops from thermal noise, while carefully timed microwave pulses manipulate the qubit states. Finally, Section 6, our quantum future. So, what does this all mean for us moving forward? Well, you shouldn't expect a quantum PowerPoint, because classical computers are totally fine for that. Instead, quantum computers are going to act as revolutionary accelerators. They'll work alongside traditional computers and AI to simulate complex quantum chemistry, design crazy new materials, and optimize massive global systems. Which leaves us with a provocative final thought. What will quantum technology offer in the coming decades? A century ago, the quantum realm completely defied common sense. But 50 years from now? Future generations will likely grow up seeing superposition and entanglement as completely normal, everyday engineering. It'll be so deeply woven into our lives that we can't even fathom it today. It just proves that while we can't always rely on our intuition, we can absolutely rely on our understanding to uncover the universe's greatest secrets. And that brings us to the end of today's deep dive. I want to thank you so much for joining me on this journey through the quantum realm. If you found this explainer helpful and fascinating, please be sure to subscribe to the channel, leave a like, and share it with a friend who loves learning about the invisible forces that shape our world. Until next time, keep questioning and keep learning.